This is the 6.1a lesson on square areas. We're going to skip the first part and go down to number 3, where we're going to create our own squares with given area. And we're going to zoom in, and we're going to start with just, even though it's not stated here, we're going to start with this square. And excuse my drawing isn't precise here, but here we have a square with sides measuring 1 and 1, and obviously 1 and 1 on the other sides, which means that the area is an area of 1. And so kind of make a list here. So we have this will be our area, and then this will be our side length, sort of like we see here. So area 1, and that would mean that the side length is 1. We're going to draw another one here, and we're going to go increase its size, and we're going to have it have a side length that is 2 by 2. So side length is 2, and that would mean then the area, and we could even break it up if we wanted to and just look at counting up the squares. Area is 4. We're going to go a step bigger. Now we're going to do a 3 by 3. And if side lengths are 3, then that means that the area, and by the way, we could probably sort of double side this because we're going to be kind of thinking about going forwards and backwards. The area is 9. But as we're doing this, the side lengths, we could do 4. I'm not going to draw it, but 4 would be 16. We could do 5, and 5 would be 25. But we are skipping over certain areas. It doesn't seem possible to draw an area with 2 square units, or 3 square units, or 5, 6, 7, or 8. We did 9. But some of these areas are not going to work out. And we need to think of this forward-backward relationship, that if we have the side length and we're going to the area, we need to multiply it by itself or square it. If we want to go the other way, we need to have an inverse operation, which is a square root. So we're going to go into this table now, and we're going to write that this would be 3, would be the side length. We could also even put like this is units squared and this is units, just to kind of remind ourselves about exponents. And if this is square units and we want to get to just units, we would need to introduce the square root, which is the inverse operation. We're going to get a bunch of really nasty decimals, and we're not going to be able to draw that square very easily, or at least we're not going to draw it this time around. And 18, although it is quite even, is also not a perfect square, or a number that we can find 2 whole numbers that multiply to equal that are exactly the same. We look at our list. 4 and 4 got us to 16, but once we go to 5 and 5, we get to 25, and we skip over 18. All right, so we didn't do all of number 3, but we got some of that down, and we're going to go to the next page, and we're going to fill in number 6. So it says, complete the following sentences and provide examples to support your statements. A perfect square is created when a whole number is raised to the second power. So perfect square, that's when we take a whole number. A whole number is 0, 1, 2, 3, 4, 5, 6, 7, and so on. No fractions or decimal, and we raise it to the second power or square. If the area of a square is A, then the side length is square root of A. That is our square root symbol. Square and square root are inverse operations or opposite operations. We're going to list out our first 12 perfect squares from our times table. 1 times 1 is 1, and 2 times 2 is 4. 3 times 3 is 9. We got 16, 25, 36, 49, 64. That was 8, 81. That was 9. 100. That was 10. 121 and 144. Those are our perfect squares. Now we're going to fill in the table, and we might even notice some of these perfect squares show up. We might also notice some numbers that are not perfect squares, which means that when we square root them, we're going to leave them with the square root symbol, and we can see that here. So if we have a square with an area of 1, we want to know what is the side length. Well, that's 1. 1 times 1 is 1. And then the next one, we don't have to draw all these pictures, but it is handy to think about that when we say perfect squares, it is literally a perfect square, or a square that could be drawn. This one is 2 and 2, which is therefore 4. So we're squaring these to go up. If its area is 3 square units, what are the side lengths? So these aren't going to be nice. They are going to be square root of 3. Square root of 13, well, if a square and square root are inverse operations, and we take this, and this is our side length, remember, and we're multiplying it times itself, or squaring it, these are going to cancel, and we're going to be left with 13. You can also look at the last problem to get an idea of where we got that. Side lengths of 20. 20 times 20 is 400. This is area of x, so that would mean that the side length is square root of x. And side length of y, well, let's think back to exponent properties. Y times y was y squared. And this one we have an area of 16x squared. So that means that we need a 4 times 4 is 16. And that takes care of that. And then we need an x times x, which is x squared. Feel free to pause the video if you need a little more time with that. But on to number 11. They give us all the areas, and we want to find side lengths, and we have some decimals here. 49 is a perfect square, so this is 7. 7 times 7 is 49. This is based on a perfect square, so what I like to do is, if I notice that I have a perfect square kind of hidden in the decimal with just a bunch of zeros, we're going to put a 7 down and place the decimal point and see if we had 0.7 times 0.7, would we get the decimal point where we need it in the area? And the trick in elementary school was that when we multiplied these, if there was 2 digits behind the decimal point, we moved it 2 places to the left. And so that's going to check out. You might also think that if this decimal was in between the 4 and 9, it might not actually be possible to do this. But they're kind of placing it such that we can do these. So this one, we have a total of 1, 2, 3, 4 digits behind the decimal point. So if I add 2 digits, not counting this 0 if I choose to write it, and I'm multiplying it by itself, and there's another 2 digits, that's going to get me the 4 that are needed. This one has 1, 2, 3, 4, 5, 6. So 1, 2, and then I need a 7, which is 3. Times itself will get me the other 3 for a total of 6. And now we're going to go the other way. So 8 times 8 is 64. This one is going to be 64, but we're going to need to move the decimal point 2 places to the left. This time we're going to need to move the decimal place because we're multiplying by itself 4 places. 1, 2, 3, 4. And this one will be a total of 6. So 1, 2, 3, 4, 5, 6. Next, we're going to simplify. These are, again, probably based on perfect squares, or if we don't know them, we could type them in the calculator. We could also guess and check. This one ends in a 5, so it probably needs to be some sort of like 15 times 15, or 25 times 25, or 35 times 35, because 5 times 5 is the only perfect square that gets me a 5 here. And 20 squared is 400, so this probably needs to be 15. 15 squared is 225, or 225 square rooted is 15. So this one is 25. You can check it in the calculator. Or you can also type in square root of 625. We did that right before break. But again, we need something that's bigger than 400. 14, we need two numbers that multiply to equal 2,500. We can ignore the zeros and just think of it as 25 and add 1 0 and think about if we had 50 times 50, would we get back to where we started? And we sure would. All right, let's think about our times table. If we multiply a number by itself, when do we get a 4 in the ones place? Well, 8 times 8 is 64. So there we go. And we said that 20 squared would be 400. Oops, 400. So this is probably 18. And it is spot on 18, but you can check that. All right. Now we get back to some Module 5 stuff with variables. A squared, square rooted, these are inverse operations, so they cancel. And we can also think of this as the fact that a times a is a to the second. So it's answer A. I need two identical things that multiply to equal 4 and x squared. So the 4 is going to be a 2, and x squared is going to be an x. So 2x times 2x is 4x squared. (64) is a perfect square. It's 8, and b squared becomes b. (19) looks like based on a perfect square of 12. So let's think about this. Here's 12, and let's see if we can place the decimal point. We have how many digits behind? 1, 2, 3, 4. So if we put it right there and multiply it by itself, that will get us the 4 necessary digits behind the decimal point. Last couple, we're going to skip 21, go down to 22, and back to the picture of a square, because this is kind of what we're doing, although we don't always draw the square. Complete the square model and simplify 9a to the 4th square rooted. All right, so we need this to be a 3, because 3 times 3 is 9. That checks out. And then we need a to the 4th, and that's going to mean that this is a squared, because a squared times a squared was a to the 4th. All right, so we finished that. This one, we need two numbers that are the same that multiply to equal 49. It's going to be 7. And then we need a variable part that multiply to equal x to the 6th. And they have to be the same, and that is x cubed. Same idea, we removed the square. We're not drawing it unless we really want to. Square root of 25 is 5, and the square root of x to the 10th is x to the 5th. X to the 5th times x to the 5th is x to the 10th. The square root of 0.49 is 0.7, and the square root of x to the 12th is x to the 6th. Last one. In fact, might be a good one for you to try and pause the video. square root of a to the 8th. Okay, two of the same things when multiplied equal a to the 8th. It's a to the 4th. And b to the 2nd becomes b. We can also over here just think, let's see, if we were to take these two and multiply them by themselves, would we get back to where we started? And we sure would, so that checks out.